Okay, thank you to be here for the lecture of today. Let me open the software of last time. Now, let me see if I'm able to find this. Probably here. Right. Yeah, this is the M file, which I presented, I think, 2 or 3 times. Let me run this M file, which we can see again that we have the system which many times, which we considered many times, characterized by the matrix A. You can find the detail in the lecture, in the first presentation. With characterized by the matrix A, B, and C, in which we are measuring the variable x1. With this variable, you remember the system results fully observable. This means without any problems, we can build, let me say, the Lundberger observer. Let me open the Simulink file. I analyzed this in depth last time. Let me just show you which kind of problems we have if I include the noise in the measurements, first of all, and then if I consider some unknown parts in the model. And then I have the possibility to go more in depth in the, let me say, in the philosophy of the observation. Just a second, because MATLAB is running. In the meantime, let me see if I find something. Okay. Ready. Look, let me now share the Simulink. Do you remember, we have seen in detail this. I think at the end, I shown you also the case with the noise, but let me redo without noise. And we have a relatively good, let me say, observation of results. I don't want to say observation because the observation of the observability is in structural characteristics. I would like to say we have a relatively good results. Of course, here probably I change. Let me the matrix A. Let me see 1 second again. I think it's not this the file. Nevertheless, I don't think so. Is this the correct file? Let me show you. This I tested the different things. Let me see in the folder. Okay, this is the exercise number 2, which I didn't show you. Excuse me. Let me see. Yeah. Let me close this. I don't have time in this course to show you. Really, I already told you about this. I mean, if I change the value, but let me. But I don't want to close. Probably have a time to tell you. Let me open the right file, which is the example number 1. It's here. This example, let me open, you can find in my study. Let me share. Okay. This here is, we can see the example number 1, as I told you last time. Let me eliminate the noise. Let me look what we have here. Yeah. I show you now what we had last time. This was the result. You remember last time I told you again how I can many times how I can accelerate the let me say the dynamics of the observer. But of course, you remember I told you that accelerating the dynamics of the observer, I increment typically this peaking effect. We will see that using Kalman filter we can minimize also this peaking effect, maintaining good result in terms of speed of convergence. Because I told you Kalman filter is an optimal approach. This means we can find a compromise. You remember I told you, placing eigenvalues of the matrix, do you remember A minus L multiply C, I can speed up, let me say, the convergence of the blue line, roughly speaking, of the observer. The convergence is an asymptotical convergence because the structure here is not a finite time observer. Now, and then we discuss a lot. Let me show you what happens if I have measurement noise. What is the meaning of I share? I think I share. Sometimes I forget to share. If I had the measurement noise, now we have some problems. We will see. The problem is not connected with the observability because the system is observable. I intend that the observability structure or the observability characteristic remain. But we will see an effect that we would basically we would like to minimize. And the Kalman filter, we will see that is exactly a structure we try to minimize this effect, which we can see in the results. Meaning of this is that what I receive from the sensor is affected by errors in the instrumentation, in the sensor, by interferences, but also if you consider a different system, I don't know, COVID, assuming that I receive the data from health institution concerning the number of infected people, and we want to estimate the susceptible people based on the model and so on. I will tell you about that. But in any case, I have projects for you. Of course, this data, which came from the health institution, can be affected by errors. I mean, look here. The true is this one. What we receive is this one from a sensor, from data which came from an institution, and so on. Really, here we can speak about the true because the system I built, let me say, artificially. I mean, I know what this is. In the practical application, we don't know exactly the system. But about that, I will tell you in 1 minute. Let me show you what happens here again. Or let me share. Of course, this kind of results, the blue results is the estimation of the yellow one. Yeah, I don't know. It could be not enough for some application. It could be not enough if you consider that here we have a 50% error, something like that. But in any case, should be nice if I can, let me say, minimize these oscillations. And the Kalman filter, we will see, tries with good results in general to minimize these oscillations and to remain around the yellow line. Or in any case, we can improve this. Of course, again, we can also consider different Lundberger observer. As I told you, Kalman filter can be somehow considered really the more advanced Lundberger observer. What happens now, as I told you before, let me come back here. If, assuming that I have a perfect sensor or the data which I receive are perfect, but I have an error in the knowledge of the system. It's exactly what I tried to tell you before. I mean, now I know perfect this, and of course, if I know perfect this, I can replicate this structure here. In fact, if you open the system here, and if you open the system here, the unique difference is the initial condition. Do you remember when I did the calculation for you? I assumed that the difference between the system, the real system, and the observer consists just of in the initial condition, the initial energy, just to introduce didactically. But really, if you remember the example of the motor, I don't know exactly the value of L, the coil, the inductance of the coil, or resistance. It doesn't matter what I consider in the system. Also, in the system like in the COVID dynamics, I will show you what I intend. We have some parameters, basically the infection rate. I don't know if you know a little bit about COVID dynamics. Did you attend my classes in differential equations? No, but I will tell you. Because we work a lot with COVID. We produce some publications with this course also after the examination. Apply the Kalman filter to estimate, and just to tell you, to estimate I mean, we have a different structure of models. This says already that we cannot know the reality. We have just a representation of the reality. This is also another problem. I mean, assuming that I am able to know that the COVID structure is represented by 2 equations and not 3 and not 4. Also, this is an assumption. How many states I will consider, but assuming that I know perfectly how many states, what I intend with state. We worked with a model which consider infected people, susceptible people. Infected means clearly, what is the number of people who result infected by COVID. Then we can consider another state which take into account the number of people which is susceptible, which can be infected. And then we can consider the people who recovered. In the people who recover, we can consider also the people who died, because when we died, we are recovered. But we can consider also people who is infected, but with latency. This means another categories of people. This means 3 states plus recovered, which is another state, in a particular state. If I consider that the people who is recovered cannot be reinfected, otherwise we have to consider another state. State means number of people. In this case, state is in a pseudo energy, because we cannot speak about energy of infected people, acceptable people, but nevertheless it's something which I can cumulate. Do you remember the new concept of energy in Kalman filter is what I can cumulate. Okay, just to introduce again a little bit some concept on modeling. I have a course in modeling and using differential equations. Sometimes I need to give you some flesh about this idea, but we will come back on this many times. Assuming that I know perfectly the system. This means, let me show you, until now we have seen a linear system characterized by A, B, C, D matrix. And this structure here, or a part, this structure here can be found in a part of the system here inside. Let me show you this. In the observer, we can see that we have the matrix A here, the matrix B here. We have the matrix L. I told you about the matrix L, the meaning of that, to place the eigenvalues. We speak about the eigenvalues because we are in the case of linear systems in order to speed up as we want the dynamics of the observer, or let me say, to reduce asymptotically to zero the error estimation arbitrarily. Look, if I change this, now why I change? Because it could be, it is, that I don't have exactly the knowledge about the system. Assuming that I am able to say we have just two states, as in this case, x1 and x2. But it could be that I don't know exactly the value or the characteristic, the parameter the parameters which characterize the model. Let me show you what is this B0. This B0, or the BO observer, let me share. It's something which does not reflect exactly B of the real system. Now, of course, I put an exaggeration. Instead of 1, I have a 7. Of course, very often, I don't remember, this one here came from here. Is this one here. 1 multiply U, I don't know if you remember the structure of the linear system. 1 multiply U is the B mat, this one characterizes the second channel, let me say, of the Mi matrix. The Mi matrix is the input map. 0 plus, we have here plus 0 multiply U, because we don't have U in the structure of this example, but we have a U here. This means the map of the input is characterized by the vector 0, 1. But of course, in the observer, which is what we know about the system, assuming that I know perfectly that we have two states and not 4 states in the system, assuming that I have an error, just an exaggeration, of course, the error is immense here. No? But of course, very often is some, I don't know, 10%, 5%, something like that. But just to show you which kind of effect which we have. If I run now this data, let me now go to the simulation. We will see that we have an effect which is not so really agreeable. Look, now, of course, it's so large, the bias, because I put 7, just an exaggeration. If you put 1,1, nevertheless, you have a bias. If you want, I show you, but not so large. But in order to conceptually to understand that if I don't know exactly the system, I will converge asymptotically, but to another value. Bias, understood? I understand the word of bias, no? I don't know the difference. We are asymptotically stable. We can try to image, but we'll never converge, or even in infinite time, to the desired value. If I add now the noise, of course, this is basically not acceptable. Also, this is not the bias error is something which we can understand extremely dangerous, because the steady state value in any case is totally wrong. I mean, just the measurement noise, even though it's not so acceptable in many cases, but of course, if the noise is Gaussian, we are more or less around the main value of the steady state value in any case. Therefore, a bias is extremely more dangerous than and Gaussian noise. But of course, Gaussian noise is also an hypothesis, but we will see this. Look, the Kalman filter we will see tries to manage these two kinds of problems. Okay. I thought that I have material to show you the example number 2. I don't know why it's not here. But I think it does not matter now. I think we can proceed showing a few words about the strange that I don't have, but anyway. The idea was to show you the example number 2, but I need too much time. Let me go ahead with a few words about the nonlinear observability, and then we will start with the Kalman filter today. Yeah. If you open again the lecture, the presentation number 1, we have 2 slides, which until now I didn't. Oh, let me see if I have it here. Yeah, it could be that I can show you this before, so I can tell you about the example number 2. Let me share this. Do you remember I told you about the concept of detectability? As I told you that really to build an observer, this you can find this equation here in the one of the last slide of the first presentation. Let me open this. In any case, I need. Now I find quickly. Let me show. Yes, let me share. Okay. Do you remember the concept of the detectability? The concept of the detectability was here. The red sentence. A system is detectable if all unobservable state vanish into 0 when time approaches infinite. This means even though the system is not observable, if what I cannot observe is going to 0, I mean, is vanishing, it's intuitive to understand that nevertheless I can build an observer. But of course, I have some limitations. Because if the system is not observable, do you remember I cannot place as I want all eigenvalues. This means the dynamics of the observer in the sense the error, the observation error or the estimation error, let me say, of course, is not totally, let me say, I cannot design as I want, no? The speediness of the error. Let me clarify this concept here. The case is exactly this. Do you remember? No, this one, exactly. If I measure the variable x2 in our original example, this easy example, which is x1, let me show you the example. This here, just to recall. If I measure the second variable, the system is not observable, but the second variable is characterized by the matrix 0, 1. But both dynamics, let me say x1 and x2, if you remember math, are stable, asymptotically stable. Because the eigenvalue of the matrix, do you remember I calculate for you, was -1, -1. I show you again if you want. Somehow, we can build the observer, but of course it's in a particular observer because I cannot state as I want the dynamics of the observer itself. So let me show you quickly. And then I have now I would like to tell you because I opened the example number 2 and it makes sense now to show you, even though I didn't upload, but I will do it. This is the example. Using 0, 1 through the calculation, I will obtain the calculation and show you many times. No? I will obtain this equation here, in which we can see that we have just one parameter to be designed, L21, because L11 disappear because of the presence of the 0 in the determinant. I told you last time this. And of course, I cannot place both eigenvalues. I can place just one. It's clear. We can see here. I cannot place both because I have just one parameter. And now, if you look at this easy example, I will upload very quickly. Now, we can see here, we have just one parameter, exactly the equation as I told you. Now, assuming that I would like to place the eigenvalue lambda1 equals -2. I can calculate L21, easy. Gymnasium exercise, high school exercise. Now, with L21 equal 1, I can calculate in this equation here, which can be written in this form, where I have the other eigenvalues. There is a theorem which I don't have time, but we can nevertheless I can show you nevertheless here that if the system is detectable, this means if the unobservable part of the system is asymptotically stable, I can find always parameters, in this case one parameter, in which both, in this case, eigenvalues are with real part, have a real part negative. This means I can build always an observer, but of course, with some constraints. We can see also here, look at home a little bit, that I have some constraints in the lambda. This means I cannot place as I want the eigenvalue, but I nevertheless exist. Here is an example, the possibility to place both eigenvalue with real part negative. This means the observer results nevertheless asymptotically stable, in the sense the error of the estimation is going to 0, but I cannot place both as I want. Let me see. We can see from here, just to comment. If L21 less than or equals, in any case, no more than -2, we have unstable. Of course, this limits the position of the eigenvalue because I cannot place both eigenvalues I want because of the limitation. Basically, we have just one parameter. But nevertheless, with one parameter, if L21 is less than this one, we can demonstrate, excuse me, larger than -2, we can demonstrate that we obtain a possible observer. Now, you can find this application in the example number 2. Which I opened, I think this one, let me see. No, this is number 1. This is number 2, I think. I will upload, but not now because I would like to go ahead with the lecture. Look, here we have a C. Let me see if this is exactly the case. Could be that is not. 0, 1. Now is the case. Let me run. We have an error because, as I told you, I cannot place both eigenvalues. Therefore, the function place does not solve, is not able to solve the problem. But now we will put exactly the case as I presented. Let me show here. If I go here inside, I can let me see. I calculate it for you. No? L21 equal 1, right? Yeah. This means I go here inside. L21 equal 1. And yeah, I can put whatever I want. This came from here. No? If everything is calculated correctly. Why I put L21 equal 1? Because for L21 equal 1, I have a lambda equal -2, if I remember well. Yeah, lambda 1 -2. And lambda 2 should, I hope the calculations are correct, equal -1, independently of L11. But L11 does not appear in the calculation because determinant govern a 0. Let me see if everything is correct. But we will see. Yeah. This is what we obtain. Of course, we have an observation. It's not so extremely bad, but of course, we are limited in the choice of the dynamics in accordance with what I told you with these calculations. This means, nevertheless, if the system conclusion, if the system is not totally or fully observable, but detectable means that the non-observable parts, about the parts, I told you a little bit before last time, but we can nevertheless build with some restriction the observer. Concluding this observability and so on, I would like to tell you a few things about, let me see, where is the presentation? Yeah. You can find in this presentation a few slides at the end considering the nonlinear observability. I will come back really in detail during the semester when I will tell you about the extended Kalman filter, which is one of the variation, one of the possible approach if the system is nonlinear. About the nonlinearity, I didn't tell you. I told you a little bit about the, of course, linear system without introducing the mathematical definition, but I told you what the linear system is and the linear time variant and linear time invariant. I try to distinguish both. Here, just a few words. We can see that in the linear case, we have a different definitions of observability. We have an observability, we say the system is observable. We have the local observability, we say that the system is locally observable, and so on. This means we can understand from this slide that the problem is extremely complex in case of nonlinearity. What the nonlinearity, in which sense the nonlinearity is complex? Because the nonlinearity is characterized by local, and we can see the word local or locally observable appear twice. And this is the characteristic of a nonlinear system in which the properties are not global anymore, but they are local. We will see together this. And we can see also another concept, weak. This means that the observability could, in the linear sense, could depend on the input. Remember, at this moment we have seen, don't care about the input. We have seen that the test is characterized by the matrix A and C. This means the dynamics through the connections characterized by the matrix A and what I am measuring. Do you remember the test? C multiply A, C multiply A squared, B does not appear. Also, independently if the system is time invariant or time variant. Very important linear. If the system is not linear, yeah, we can see from this, I am telling you that the concept depends, or the test depends on the input too. We come back on this. The test is extremely complicated to be explained, but extremely easy to be done. This means I will do when we will consider the nonlinear systems. Okay, now please open if you want the lecture of the Kalman filter, which is my study. I will upload the example number 2. I will upload it this slide, but later at the end of the lecture, because I would like to go ahead. So we have also this simulation of detectability, this idea that I cannot place all eigenvalues as I want, but nevertheless, even though the system is not observable, I can build somehow. I can do. We have seen that it works, but of course, it could be that it will not work as I want, because the dynamics, the eigenvalues in the sense, cannot be placed arbitrarily. Look at now at the second presentation. The second presentation looks like something like that. Let me share in 1 second. Look, linear. We are in the linear case. Discrete Kalman filter as a state observer. About the Kalman filter, I told you roughly at this moment. Discrete is something probably which I need to clarify, but we have an example. We have an example in order to clarify at the beginning discrete. Before clarify the word discrete, again, the literature. Now, I think starting from next week, we can really, you can really download this file here, which we have in the summary of these 5 equations, linear and nonlinear. We will see nonlinear later. Of course, it's in a compact paper, but I think my goal is that in the couple of lecture, I think next week, you can really try to understand what is written here, even though it's extremely compact. As I told you, this paper here is a good paper for students who already know Kalman filter. But I think we can already next week. You can already next week download look at this content here. Yeah. Goal this week, this part of the week, the lecture, and next week, of course, to show you the 5 basic equations which characterize the basic structure of the Kalman filter. We can see here at the end of this slide, two sentences in the frame, in the red, let me say frame. Very important that detailed knowledge of the system is not necessary to build an observer. And of course, we will see that at least at the beginning in this course in particular, that we need some hypotheses, but more advanced versions of Kalman filter try to remove also some hypotheses in general in order to relax, not to apply in different contexts the Kalman filter. In any case, under some conditions, in this course at least we will see, we have an optimality of the observation, and we estimate. Estimate is already connected in the literature with the optimality. Of course, we can understand this concept of optimality because, as I possible to say, when we have the problem to be solved, when we have a mismatch, very often we have to find a trade-off. Very often we have to remember also that the problem of the picking. Fast observation or the estimation, observation and the Lundberger structure, we have a high picking. This means I am converging very fast, but at the beginning I have to pay the price that you have a big error. Remember, I showed you this peak. And of course, it seems to be something structural, no? Very fast, but observation, but very high initial error, or a very large initial error, because the system is quite nervous, it's quite prompt. Now, of course, this it seems to be very intuitive to say, it seems to attack this problem, to reduce the peak, to nevertheless to maintain an acceptable time of observation. It seems to really be an optimal problem. We try to find a compromise. Kalman filter tries to find a compromise in the presence of these two, also in the presence of the picking, because it's connected nevertheless with the dynamics, but in particular because the picking problem, all problems which I told you, picking, noise in the measurements, something which is unknown in the system is not basically totally solvable. But Kalman filter try to find a compromise and try to propose possible solutions. Or solutions, because we will see we have many let me say variation of Kalman filters. Yeah, I think this concept of unknown is now to be considered, and we can see also the second sentence here that the discrete form of the observer allows to realize the prediction, which is also an important point in the Kalman filter. This point is not so important in different structures of observer prediction. I realize an observation, even though something is unknown, noise in the measurements, or structure uncertainties in the system, what I don't know in the system, and realizing a prediction which is the kernel, let me say, of the Kalman filter. Yeah, you remember the system here? Continuous system. I don't want to go in depth again on this, the motor. I measure the current. I want to observe current and velocity. Now, a few words about the discretization, because the discrete or the discretization plays an important role in each observer, but in particular in Kalman filter because of this prediction. You remember, until now, I told you about the discrete, just showing you in a scheme parallel to the continuous in the context of Lundberg. If you want, I show you again. As I told you, in Lundberg, at least if you look at the picture, we cannot realize just in the notation, we cannot realize any differences. And but nevertheless, the dynamics is totally different. Lundberg continuous is a dynamic totally different to a Lundberg discrete. I don't have time to show you the Lundberg discrete, but I will introduce here some concepts related to the discretization in order to introduce the Kalman filter. Discrete dynamics are totally different with respect to continuous dynamics. Totally different. What is the discrete dynamics? Let me look if I find something to show you quickly. I don't know why this slide is not here. You see 1 second, why is that we? I will do it. Yeah. Before doing, let me tell you, let me introduce this slide. These two equations, I told you about these two equations which represent the model of the motor. Anyway, we have a model. COVID model, economical model, whatever we want. Now, this model here is a continuous one. I mean, the current, the velocity, the input voltage change continuously over time, or at least we, it seems, it seems to be that change continually over time. Why it seems to be? Because we perceive that we perceive continuous. But if you remember, I'm not expert, of course, the quantum physics, it seems to be that the reality is not totally continuous. But anyway, this is more philosophical aspect, but not only philosophical aspect. But we perceive that the velocity, if you look me, seems to be moving continuously, the book. But anyway, I don't want to go in depth on this because I don't want to say something strange. But in any case, we assume, or we perceive the reality in continuous form. The velocity, position, anyway. The computer, let me say the Kalman filter, which is nevertheless implemented, we will see in the computer, the microcontroller. The Kalman filter describes this reality in discrete form. There is also observer continuous. Of course, what we did until now, also today, the simulation, it seems to be continuous. Conceptually, it's continuous, but it's implemented discrete because this computer is characterized by a clock, by a microcontroller, which is working in discrete form. This means continuous for us today, what I have told you today, means that the sample time, you can see here this concept of the sample time at the end of the slide, is variable, but we cannot, let me say, is variable, but this variability is fixed, variable fixed. The variability is in the computer. The MATLAB realizes the suitable TS, sample time. It seems to be everything continuous. We can nevertheless really realize continuous. I don't know if you know operational amplifiers. Calculators realize with operational amplifiers. Let me say, this is more continuous than the microcontroller, because it seems to be that also the quantum theory is also try to explain also the transistors and so on. Forget this, but just to understand at the end of these sentences, what we have here in the second part of the slide is a representation of this possible representation. What the reality is, well, God knows. We perceive something. But this is a little bit philosophical sense. But anyway, mathematically, no errors. I have these expressions. Here I try to explain using Lenz's law, Lorentz law. You remember in the first lectures, using electrotechnique, the knowledge which we have a mathematical, physical mathematical representation. I don't want to go in depth if this is good, if this is bad. Anyway, what I'm writing here, first of all, I try to characterize in a possible discretization. Forward Euler discretization. Forward is the word which recalls me if I can consider a forward Euler, it could be that I have a backward Euler. Forward, go ahead, backward, go back. It is. This is the case. We have also a backward Euler. We will work here almost always, I think, just with forward Euler, but we can work together in the project with different discretization. How many discretizations I have? Forward, backward, point, Runge-Kutta 1, Runge-Kutta 2, Runge-Kutta 3. I don't know if you heard about this. Runge-Kutta methods. It's the way to discretize different algorithms. Why we have many discretizations? We have many discretizations because no one is good. To be more precise, all are good if you want, but of course we have different systems, we have different dynamics, fast dynamics, slow dynamics, with many equations, few equations. Of course, the mathematicians, the applied mathematicians, try to think about different ways to discretize, because this is a possible representation of the system here. But we can realize this also trying that sometimes we need some different assumptions and so on. Which assumption we have here, this representation? Look, the current I, the velocity omega on the input U is characterized by, or better to say, is samples in this form. I of t equal I of k minus 1, which everything multiplied ts. Formally, the nomenclature is compacted in this form in which we didn't consider ts, even though ts is there. I mean, as normalized, ts is fixed. Sample period. I will show you now a little bit better what I intend. This old for I, omega, and U input. K is an counter, is an integer. I didn't put here, but n recall as the integer, 1, 2, 3, 4, and so on. Very important. Look at these two derivatives. I approximate the derivative of the current in this form, I of k minus I of k minus 1 divided ts. The same for omega. Let me draw for you what I intended so we can understand clearly. Okay, I write it. Oh, I forgot to. Let me. I didn't connect. 1 second. Probably you have seen this also in gymnasium. I don't know. Let me do something like that. Yeah, this is our TS fixed at this moment. Could be also variable, but let me fix at this moment. And we approximate the signal, this continuous signal within a stepwise constant function is here. The derivative is approximated, as I told you, this level here minus this level here divided Ts. If you remember, assuming that is E of t. And in the meantime, E of k. We have E of t, the continuous, E of k, the stepwise continuous. Now, if you remember, the derivative of E of t was at each k, defined in this form. This means, for instance, if this is k, I of k minus I of k minus 1 divided Ts. Now, please pay attention, it's a little bit philosophical now. I can do the same for omega and so on. If I of k is the future, I of k minus 1 is the present. Let me say more easy. If I of k is tomorrow, I of k minus 1 is today. Now, question. But if I were to approximate the derivative of the current tomorrow minus today, I know just today. Tomorrow I don't know. Consider this a little bit format, but if you don't like, consider a different way in which I of k is the present and I of k minus 1 is the past. The sense makes sense also practically to calculate. But it does not matter which you, as you consider, because formally the idea is to build, in any case, in a prediction. Of course, in this sense, we can build in a prediction, says today is the present. I predict the present. I can predict the present considering today minus yesterday. But of course, if I already know today is not possible, that doesn't make sense to speak about prediction. Therefore, I would like to insist on this prediction which I introduced in the first slide. Think about tomorrow minus today is the approach of forward divided 1 day. TS is 1 day. But TS could be TS depends on the dynamics of the system. We come back on TS many times. I will come back TS many times. Sometimes it's fixed by the system itself, fixed. Example, in economics. If you sign a contract with a bank in which the interest is paid each month, TS is months, because in 1 month, if you don't do anything, your money will remain the same. So I will come back on this. I will show you a little bit also an economical system. In some cases, fixed, yes, we cannot change. Or if we change, does not, I mean, we can change, but we have to be careful in this sense. Because we have an TS which is structured in the system. If the system is discrete, the case of the economical system is clear. Also in COVID, in the project which we did, we received data from the health institution each day. This means TS, we change the value each day. In stepwise continuous, stepwise continuous form. Because the system appears structurally discrete. Yeah, the idea is to build I am concluding, to build a prediction. And in this sense, we can speak about future minus present, even though you cannot think about a real approximation of the current. Here, to be precise, I have to write circa, but I wrote plus as in many books because now I plug in here. I plug in here. But of course, here is circa. As in Gymnasium, we approximate always the derivative. The difference divided when this different happens. The gradient, you can call in many forms. Think about future minus present, because here it seems to be the present, but not in the sense to approximate, but in the sense of prediction. Of course, we cannot calculate. Now, if I plug in here these 5 assumptions, I will obtain, believe me, these 2 equations in the red frame, in which now we have the prediction. We can see ik is a function of ik minus 1, omega k minus 1, u input k minus 1, and the same I can say for the dynamics. I use this word of omega. Of course, everything together with the parameter of the system and Ts. Very important. Ts nevertheless characterizes the dynamics of the discrete representation of the system. This means if I have a discrete system, and if I use an Ts which does not reflect the discrete system, we have to be careful. I will tell you about that. I mean, in the example which I told you, if the liability, the interest change each month, I will consider each day, no problems, because it just, I sample in a redundant way. I look for 30 samples, does not change anything. But if I sample the system more than 1 month, then it could be that I will observe, I have an information, I can lose information, or at least I can lose when the information exactly change. Just to understand. But nevertheless, Ts change the dynamics. If you consider Ts variable, as in the case of motor, change the dynamics. Very important, because I will tell you something in next week, concluding that I can build everything using matrices, as I told you in the continuous form. This information here, these 2 information here in the frame can be written in matrix form. We have seen in the first lecture, I think, in continuous, not in discrete. In general, I can build for linear system, just for linear system, forward Euler approximation using directly the matrices. We will see that you don't have to learn these methods, because we will come back on this nevertheless, because MATLAB does alone everything. If the system is not linear, we don't have this recipe. Backward, very shortly, and then next week. No, let me do 2 minutes more. I told you that exists backward. I told you exists longitudinal and many other methods. The difference is exactly what I am considering as present. In backward, instead of k minus 1, actual value, the present value is k. Basically, here, to virtual approximate the derivative of the current. Virtual means it's connected with forward because I'm considering the future, or better, let me say, the present minus the past. No, so it's more concrete. Um, let me tell you about this virtual. This is not concrete, but clarify better the word forward. If this is the present, I can approximate virtually the derivative of the current, the future, minus the present. I look forward. I look forward to approximate virtually the current. If I am considering Ik is in the backward, the actual value, I look back to approximate the derivative. It seems in a formal difference, the approximation is totally different. Totally different. We have two different Kalman filters using two different discretization. We work with Rolls-Royce in the full project in using backward Euler. I have a paper I can show you very shortly, and then we conclude. We will come back on this. Probably you have seen this kind of possible approximation of a signal from the upper part, from the lower part. The lower part is forward, from the upper part, red is backward. I don't want to go in depth. This I will come back probably if I have time. In some project we can do together eventually. The backward Euler, when we can use the backward Euler in case of stiff system. When we have two eigenvalues or two dynamics in case nonlinear, one very fast, one very slow, but now I cannot clarify why. 1 second to conclude to introduce the lecture of next time. Kalman filter. We can see from this possible scheme, we have everything discrete, A equal AK, B equal BK. In this paper, we consider A equal AK, B equal BK, XK, UK is the sample signals, states vector input. We will see together next time the dimensions on. Very important here, the new thing with respect to what I have seen until now, that we introduce a system noise and a vector we can see with the same dimension of the state, which try to get what I don't know about the state. System noise means this is a Gaussian vector at this moment, or that vector with Gaussian variables or the components. The hypothesis we will see next week, Gaussian is important for us. We will go ahead for the whole semester with the Gaussian hypothesis. We have also Kalman filter without this hypothesis, in which we relax this. We do the same, this to get something which I don't know in the system, which characterize basically the dynamics, xk. And we do the same also for the output equation. It's now, instead of y, we call the variable z. Instead of c, we call the variable h. We don't consider d. Do you remember I told you also last time? In this course, d is equal 0, but in some project we can do together, if d is not 0, the representation of the output. It could happen. It's not in a big extension, in a complex extension, but I would like to simplify the lecture in this form. Look, VK, the name is measurement noise, characterize the noise which can be introduced by the sensor or the uncertainties in the data. This is extremely important because you remember is an optimal approach. We try also to manage the problem of the picking and the estimation time, but in particular, the unknown related to the system, and the unknown, which I don't know, related to the sensor or to the data, and so on. Question. what about the discretization noise? Open question. Could be included here or could be included here. We have seen that we have an approximation of the thing. The real word we think about is in continuous. And I represent in discrete form. Also, this is in an error, is a mismatch. Think about it. Thank you to be here. If you have a question, we're here for you. Otherwise, we will see next week. I think next week, really, I show you quickly these 5 equations so we can start to simulate, because otherwise it's quite, I think we can understand better with the equations, with the MATLAB. I'm here for you for any questions, technical questions or organization. I will fix next week this office hours, so we can eventually per Zoom or per directly to speak together. If the schedule is not okay, we can arrange a meeting directly in another time. Okay. If no technical questions, if no other question, I close now the lecture.